Welcome to ePathshala lecture series on computer science. In this module on data analytics, we will be discussing about data analysis foundations based on probabilistic and Bayesian theorems. So, the learning objectives of this module are to learn the fundamentals of probability theory, understand the probabilistic analytics with examples, and to learn the application of Bayes logic for analytics. First, let us start with the fundamentals behind probability theory. So, what is a discrete random variable? We can consider a variable A which is Boolean valued as a random variable if A denotes an event and there is some degree of uncertainty as to whether A occurs or not. For example, A can be treated as a random variable which may be associated to who will be the PM of India in 2020, or we can call A being associated to a scenario the PM of India in 2020 will be a female, or we can consider A to be a random variable which may tell when you wake up tomorrow will there be a headache or not, or A can be treated as a variable which indicates you having a swine flu. Now, how exactly we can know about this is, first we should know what is a sample space for this. Suppose we have a set S which highlights all possible outcomes of a particular experiment, then that set S is said to be a sample space for the experiment. So, here from this diagram, say the area indicated by this box will indicate all possible outcomes and the circle indicates the set of possible outcomes associated to the given sample. So, here the elements of this sample space are called as outcomes. Now, let us understand this with examples. Consider a coin. So, a coin will have head or tail. So, the sample space for a coin flip will have two outcomes, one is head, another one is tail. Consider a dice. The sample space for the die roll will be the numbers ranging from 1 till 6, or we can take a deck of cards and now we can identify a sample. So, a sample space for a single draw from a deck of cards will be this set. So, the set may have ace, spade, ace, clever, ace, heartin, ace, diamond. Then we have cards with number 2 in spade, clever, heartin, diamond and so on. Finally, we have the card with king, spade, clever, diamond and heartin. So, this entire set is said to be the outcome, which is nothing but the elements of our sample space. Having understood what is a sample space and outcome, now let us get to know what is an event. An event of any subset S, that is the whole set itself may be considered as a subset of the S, is called as an event. So, for example, from a deck of cards, we know what is the sample space. Now, from this sample space, we can identify say a set of outcomes. For example, here in this scenario, it can be an event where we are selecting card associated to jack. So, these 4 outcomes which is part of my sample space will be treated as an event. So, we have understood what is a sample space. So, sample space is a set of outcome. An outcome is actually a possible world, an event is a set of outcomes. Now, we can actually understand this event from a mathematical perspective. If there are 2 events A and B, then they exhibit a property mutually exclusive. If A and B are mutually exclusive and A union A2 union A3 till AN is going to be part of the set, then the collection A1 till AN forms a partition of S. Now, why this is essential is, whenever we are trying to analyze a sample data, the sample data may be considered as partition of the outcomes. So, each and every partition in term may be analyzed for deriving subsets data or inferences, and these inferences may be put together for arriving at a conclusion about the whole data. For example, all the outcomes of drawing say a card from a deck of cards will result in partitioning of my outcome or my sample space. So, here I have 4 partitions. One partition is about cards related to hearts, another partition is about cards related to clubs, another partition is related to cards having spades, and the fourth partition is all cards having say the diamond. So, these partitions actually are part of your original sample space. So, now let us define how this sample space may be used for defining probability. So, given a sample space S, a probability function may be defined which maps each event S to a real number, and this number must satisfy the following, that is, probability of A must be greater than equal to 0 for any event A which is part of the sample space S. Probability of the whole, that is the sample, must be equal to 1. So, all the probability related to all events of this sample space put together will be equal to n. And for any number of mutually exclusive events, we end up with probability of A union, probability of A2 union, probability of A3 as probability of A1 plus probability of A2 plus probability of A3 and so on. So, the overall probability for mutually exclusive events is going to be sum of individual probabilities. So far we discussed about 4 definitions: sample space, outcome, event and a probability event. An example for sample space may be the card that you draw at random from a deck of card. An outcome can be say one single sample from my sample space. An event can be say a card which is read from the given deck of card, and the probability of E, say for example, what is the chance of drawing a red card, which is indicated as probability of red, for example, it is equal to 0.5, or what is the chance of drawing a black card is equal to probability value 0.5. So, events are quantified using some number. Let us take an everyday example. Assume you are a doctor. So, patients visit you at regular intervals of time. Now, we can construct a sample space, and this sample space indicates all the patients who have visited you on a day or in a given day. Now, what may be an outcome from this sample space? Outcome, as I already mentioned, is going to be a subset or say one entity from the sample space. So, I can choose a patient who may be a non-smoker, a female, diabetic and might have had headache, or I can choose another outcome which is associated to an individual or a patient who is a smoker, his sex may be male, he may have back pain, schizophrenic, and he may be associated with delinquent medical bills, etc. So, now when I choose a patient, that patient becomes an outcome for the given sample space. Now, what is that we are trying to do is, if we assume the number of patients who visit is going to be 100, then the patient sample space will be equal to 100. Now, what is that we are trying to do here is, now we are trying to verify whether these patients are equally likely to occur. Practically speaking, it is not so. So, then what is that we need to assume is, we assume that these patients equally likely occur. In other words, they all have equal chances or equal probability. Now, there is an event, assume a patient has a flu, and this event is represented using the set F. Now, what is that we are trying to do is, we are trying to identify how many number of patients have flu. Assume the number is 2, that is exactly 2 from your sample set are patients who also have a flu. Since our sample space size is 100, now we can determine what is the probability of a patient having flu from the patient space, that is from our given sample space. For this, we need to know the number of chances favorable and the total number of chances. Here the number of favorable events are the 2 patients who have flu, and the total number of chances is nothing but the total number of patients. So, it will be 2 divided by the total number of patients, which is my patient space. So, which is equal to 0.02. So, we are trying to define an event based on its probability or chance, and this chance will help us to quantify the probability of a given event. Now, let us understand, having understood a simple probability, now let us understand what is conditional probability. Assume you are given with a sample space which indicates all the patients who visit your hospital or say your clinic on one day. Now, there are few patients who have flu. So, the chance of patients having flu is indicated by the respective probability P of f, which is equal to 0.02, which we have already discussed. There is also a chance that few of the patients have headache. So, the probability of patient having headache is say 0.1. Now, from the given sample space, we identify there is an overlapping between patients having flu as well as patient having headache. So, this is indicated by means of the overlapping area in the given set diagram. So, the circle indicates patients with headache, and this ellipse indicates the patient with flu, and this overlapping region indicates patients having headache and flu. Now, what is that we are trying to say here is, we are trying to do an analysis that may help us to understand, better understand, is there any relationship between having a flu and headache. Now, what we are trying to do here is, we are trying to identify if a patient comes with an headache, is there a chance for the patient to have a flu. So, this is called as conditional probability. So, here we are trying to define if a patient has got flu, so this event has occurred. We are trying to find the chance for the patient to have an headache. So, how this notation, probability of H given F, may be read as fraction of F's outcome which are also in H. So, how this may be determined is, we know what is the probability of patients having flu, that is 0.02, what is the probability of patients with headache, that is 0.1, and the overlapping region is determined by this conditional probability. Probability of a patient with the flu also having an headache is 0.50. So, now we are trying to determine this probability based on this equation. So, here in this equation we try to identify what fraction of patient with flu is associated to headache. So, this will be equal to number of favorable events divided by total number of events. Here the number of favorable event is the number of patients with flu and headache divided by the total number is the number of patients with flu, which is nothing but the region associated to the overlapping area, that is where we have H and F overlapping, divided by the region occupied by this particular region F. So, which is nothing but probability of H and F divided by probability of F. So, this is what we called as conditional probability. So, how we can now define conditional probability is, if there are two events A and B, and now these two events are associated to the sample S, and the probability of B, that is the second event, is greater than 0, then we can define a conditional probability of A given B. And how this may be written is probability of A given B. So, here the event B has already occurred. Now, we are trying to identify what is the chance of A to occur, which is equal to probability of A and B divided by probability of B. Now, this may be applied as a chain rule, and say the simple rearrangement of this equation will result in probability of A and B is equal to probability of A given B multiplied by probability of B. So, this is what is used for probabilistic inferencing. So, now we can identify, say for example, one day we wake up with a headache. Now, based on this probabilistic data, we may assume that 50% of flus are associated with headache. Therefore, the chance for me to have or ending up with a flu is 50-50. So, how we can determine this is from this conditional probability value. So, we have identified there is 50% chance for a patient who comes with a flu might also have headache. So, with this conditional probability, now I can come to a conclusion that if I have a headache, then I can conclude there is 50% chance for me to have a flu. Whatever we have concluded, we will have to first verify whether it is correct or not. So, here the reasoning that you have made, whether it is correct or not, needs to be analyzed. So, how this may be analyzed is using the conditional probability. So, as indicated in the previous slide, the conditional probability will take this equation. So, here we have probability of a person having flu, the chance for the same person to have a headache is 50%. The probability of patients having flu is 0.1, which is 10%, and the probability of 0.02%, which is equal to 2%. The probability of patient having headache is 0.1, which is 10%. So, now if we substitute these values into this equation, we have a value 0.10. In other words, the chance for me to have flu given headache is just 10%. So, the reasoning that we made earlier, that is there is 50-50 chance for me to have flu, is wrong, and this may be validated using the conditional probability scenario. So, what is that I am trying to say here is conditional probabilities will help us in doing better reasoning. So, in an analytic environment, if you are adapting conditional probability, we can actually make use of conditional probability where we have variables that are determined by another variable. So, one attribute may be conditionally dependent or independent or another variable. So, in such scenarios we can make use of conditional probability for better inferencing. So, whatever we did till now is actually associated to say Thomas Bayes. So, Thomas Bayes actually gave up this rule or theorem, which is called as Bayes theorem. It is famously called as Bayes rule. So, what exactly this Bayes rule states is probability of B given A is equal to probability of A given B multiplied by probability of B divided by probability of A. Having understood what is simple probability, what is conditional probability, and inside that we have understood what is an space, sample space, outcome, event. Now, we will understand how this conditional probability and Bayesian theorem may be useful for analytics. Actually speaking, this Bayesian theorem or logic is actually a type of probabilistic learning. In probabilistic learning, what we do is we try to calculate explicit probabilities for hypothesis and then we validate the same. In certain scenarios, what happens is whenever we get a data, we try to update the explicit probabilities in an incremental fashion. Therefore, application of Bayesian theorem results in a probabilistic learning which is going to be incremental in nature. This Bayesian theorem and its application will be useful for prediction problems. So, we may end up with a probabilistic prediction wherein multiple hypotheses which is associated to more than one variable may be proposed and validated using standard probability theory. This Bayesian logic or theorem is actually considered to be a standard application in analytics. The reason, since it is going to be incremental and the computations that we do depends on the instances that is provided for the learning scenario. Therefore, we normally end up with optimal decision making when we are using Bayesian methods for analytics. Now, let us see how this Bayesian theory may be applied for analytics. In analysis, normally this Bayesian theory is used for classification. So, it is called as Bayesian classification. So, in Bayesian classification, what normally we do is, given a training data D, we will be learning, in other words, we will be building a classification model. Based on the classification model, we will try to identify rules or we will try to predict a class label for any new data. So, what we do is we take the data, we propose a hypothesis, the hypothesis is nothing but an outcome of the model, and then we try to justify for which particular data the conditional probability is high. So, when we apply Bayesian theorem, what happens to this classification problem is we try to identify what is the probability of the hypothesis given the data, which is in turn defined using the equation what is the probability of the data given the hypothesis multiplied by probability of hypothesis divided by the probability of data. Whenever we are working with respect to a standard set of data, there may not be any variation in terms of the data. Therefore, we can treat the probability of the data to be constant. Now, what happens is we need to worry only about the numerator, the parameters which is part of this equation in the numerator of this equation. So, the numerator is associated to two probabilities, one is probability of D given H, another one is probability of the hypothesis. So, now all that we need to do is identify the probability for an hypothesis which is maximum, and the hypothesis which has got the maximum conditional probability will be used for further classification or prediction problem. What may be a practical difficulty in this Bayesian classification environment is we require initial knowledge or we need to calculate many probabilities values. Since we are computing probability values, the total time taken as well as the computational cost will be high. But in say a very large parallel processing environment or multitasking environment, such computations only take less time. So, therefore, how we can proceed with Bayesian classification? So, first we need to formalize the classification problem. Here in classification, all that we are going to do is take an unknown data x, assign it with a known class label. So, we need to identify what is the chance that a data x may be assigned to a given class label, which mathematically may be represented as probability of C given x, where C is the class label and x is the data. So, which indicates the probability that the sample tuple x is of class C. So, the idea here is we need to identify one class for which this probability is maximal. So, how to estimate the posterior probability? Now, when we apply Bayesian theorem states that what is the probability that an event x given another event say y has already occurred. Here in this classification scenario, the data is what we have, so which has already happened, and we are trying to predict what is the chance of the data to belong to a class label C. So, which is equal to probability of x given C multiplied by probability of the class label, the whole divided by probability of data. As I already mentioned, probability of data is going to be constant for all classes. Therefore, we can ignore the denominator component. All that we need to worry about is the parameters in the numerator. There are two parameters in the numerator. Among these two parameters, we need to identify which parameter can help you in maximizing this product value. Probability of class is also going to be fixed. The reason, if we have two classes, accordingly the probability value may be fixed. The only other parameter with which we can maximize the numerator value is probability of x given C. So, all that we need to do is concentrate on these two probabilities, probability of x given C and probability of C. Let us understand this with an example. Consider a data set. This data set provides you information about environmental parameters, weather parameters like outlook, temperature, humidity, and whether it is windy or not. Based on these attributes value, finally it will tell you whether tennis can be played in such an environment or not. So, the class label here N indicates tennis cannot be played if such weather condition prevails, and the class label P indicates tennis may be played for such weather conditions. Now, we need to apply Bayesian theorem here. As I already mentioned, for all the data, we need to first identify two important probabilities. One is the probability of the class label, another one is probability of class label with respect to the given data. Here in this scenario, there are two probabilities for the two class labels. One is class label S, that is indicated by P, another one is the class label No, indicated by the class label N. So, the probability for class label P is 9 divided by 14, which is a simple probability, where 9 is the number of records in which you have a class label P. So, among these 14 records, there are only 9 records in which you find the class label P. So, therefore, it is 9 divided by 14. Probability of the class label No is number of records in which you have the class label N, which is equal to 5, divided by total number of records 14. Then we need to compute what is the chance of the class label with respect to each and every attribute's value. Since here in the given example we have 4 attributes, we need to compute the conditional probability of these attributes with respect to the class label. So let us take the first attribute outlook. For outlook there are 3 possible values, one is sunny, other one is overcast and the third one is rain. So for these 3 possible values we need to compute the conditional probability with respect to the class label n and with respect to the class label p. Now let us take the class label p. Identify those records that contain the class label p as well as the outlook parameter sunny. So now among these 14 records there are only 2 records that satisfy the given constraint, that is it must have both the class label p as well as the outlook parameter sunny. Yeah, this record containing the outlook parameter sunny also having the class label p, and the other record, that is the 10th record, also containing the outlook parameter sunny and the class label p. So total number of records that satisfy both class label p as well as outlook is equal to sunny is 2 divided by total number of favorable events. Here for the class label p the total number of favorable events is 9 because only 9 records contain the class label p. So the probability will be 2 divided by 9. Similarly you will have to compute for the outlook value overcast and the outlook value rain. Once we have computed the probability with respect to the class label p, then we will have to calculate the probability with respect to class label n. So now take those records that contain the class label n, there are 5 records. Identify among these 5 records how many records contain the outlook parameter sunny. So here you find the first record containing outlook sunny as well as class label n, the second record also containing outlook is equal to sunny and class label n, and finally we have say the middle record, that is the 8th record containing the outlook parameter sunny as well as class label n. So it will be 3 divided by 5. Similarly we calculate for the other values of outlook overcast and rainy with respect to the class label no. So we have understood how we can calculate the conditional probability of a record with respect to a specific class label. We have computed for one attribute, we will have to compute for the rest of the 3 attributes also. So similar to computing conditional probability for outlook parameter, we will have to compute the conditional probability for temperature with respect to the class label yes and no. So the conditional probability is given here, so this is your conditional probability table. Having computed these many number of conditional probabilities, now when a new record is given we can easily identify to which particular class this record may be associated to. Assume the given scenario is a record x having a value rain, temperature hot, humidity high and windy is equal to false. Now we need to identify which class label may be assigned to the data x. So as per Bayes theorem we need to calculate the product of the probability of x given p and the probability of p, similarly for the no class label. So the probability of x given p is nothing but the individual probability of the attribute called outlook, attribute called temperature, attribute called humidity and attribute called windy with respect to the class label p, multiplied by probability of the class label p. All these probabilities we have computed earlier, we can just substitute the corresponding values and calculate the total probability. Now among these 2 probability we need to identify which probability has got the maximum value. Now we find the probability associated to the class label no has got the maximum probability. Therefore we can predict the class label for the given data x is n, that is for the given weather conditions tennis should not be played or it will recommend do not play tennis. Now this is how we can apply Bayesian theorem for the purpose of classification scenario. So to summarize, in this module on data analytics we discussed about how probability theory is essential and may be used for analytics, inferences based on probability theory how may be effective for decision making, and finally we analyzed how analytics may be achieved based on Bayesian theorem and how it is widely used in classification environment. Thank you.